go. All right, so we had those problems from yesterday. We're going to look at the predicting the graphs, position, time, velocity, time, and acceleration versus time.
Thank you.
Here's that. Try this right here. For each of those cases, the first case we have is where the ramp is set up with the origin at the top of the ramp. The cart's going to roll down the ramp. And real quick, we look at position, velocity, time for that. And acceleration time. As it goes down the ramp, the position should start at 0 and do what? What do we think? Describe it. Use your words. Should be parabolic, we think. What about the velocity? Should be linear, getting bigger or smaller?
Bigger.
Right? Should be moving faster as it goes down the ramp. That makes sense. What about acceleration?
Positive.
Should be positive because it's moving in the positive direction. And should it be constant or changing?
Constant.
Acceleration should be constant. So it should look something like that. We will look at those graphs. Yeah, while I... So looking at that first graph is my position graph. Does it match what we think?
Mm-hmm.
So if we look at the velocity graph, is it linear? Like we expect? It is. And the acceleration graph? Oh, that's not what I want. Graph 3. Acceleration, constant and pretty much positive. Is everybody good there?
Mm-hmm.
All right. So if we look at then the next setup, which was with the origin at the bottom of the ramp and the cart starting at the top, and it's going to go down toward the origin. For our position time, velocity time, and acceleration time, how's it going to start in terms of initially? Where's it going to start in relation to the origin, which is at the bottom of the ramp? On the positive side or negative side? Positive side. And how is it going to move? Where's it going to move when I let it go down the ramp? Toward the origin or away?
Toward.
So it's going to be going toward the origin. Is it going to be going faster toward the origin or slower toward the origin? And what would one of those graphs look like? Faster, which means what has to happen? Which way is it going to curve? Is that a curve of going faster toward the origin? As opposed to this, which would be going slower toward the origin, right? Velocity time starts at what? Starts at 0. And what happens to it in terms of meters per second? In which direction? Does it go the same speed down the ramp?
No.
So it goes more meters per second. And which direction is it going in?
Negative.
So where should my velocity go from here?
Down.
This way
No. Through.
or this way? Should go down, and it should be ever increasing, correct? What about my acceleration? Is it positive? Why negative? Right, because my object's moving ever increasing velocity in the negative direction, so my acceleration should be negative. If we look at that, So my velocity graph looks just like we thought. My velocity graph starts at 0, straight line down. My acceleration graph, negative, and pretty much linear. Is everybody good there? And the last one was starting at the bottom of the ramp and being pushed up, right? Yes or no?
Yeah.
So if I start at the bottom of the ramp and it is pushed up the ramp, what should the position time look like there?
Parabolic.
Should be parabolic, and what should that parabola look like? Should be getting faster, slower,
Slower.
until what happens? For the briefest moment of time, it does what?
Stop.
And then what does it do?
Slows the other way.
Rolls back to the origin, getting faster or slower?
Faster.
Make sense? Velocity time. Where's my velocity start at? When I push it up the ramp, is it going, which way is it going? If my origin's here and it goes that way, it's that positive or negative.
Positive.
My velocity starts positive. Does it speed up, stay the same, or slow down?
Slow down.
Slows down at the same rate? Or does it slow down really, really fast and then slower, or all right, the same rate? And then once the velocity reaches 0, what does it do?
Becomes negative.
It starts going back negative, correct? And as it goes negative faster and faster and faster and faster, right? And my acceleration, which direction is the velocity changing all the time? My velocity goes from fast to slow, right?
Mm-hmm.
Which means acceleration would be positive or negative.
Negative.
And then my velocity goes from slow negative to fast negative. So my acceleration is negative, right?
Yes.
Positive acceleration means be going somehow changing velocity going that way, right? But in this case, it's always changing velocity that way, slowing it down and speeding it up in that direction. So my acceleration should be negative. Does everybody agree with that or have something different to say? Let's see if we can figure out how to get this to work right now. So my position, parabola back to where it started. My velocity, down and continuing to get bigger. My acceleration, negative the whole time. Is everybody good there?
Mm-hmm.
Now there's the last one on the sheet that mimics the first one, right? The ramp down, and then it goes flat. We already looked at the ramp down, correct? The ramp down. The velocity was, or the position time was increasing parabolically because it was going faster and faster and faster. The velocity time was increasing at a linear rate, and the acceleration down the ramp was positive. Now, let's say that, let me take it all the same. So this point represents where I go onto the flat portion of the track after the ramp, right? How would my position change on that flat portion as it went away from the origin? It would Let's assume no friction. But would I continue to go away from the origin? With no friction, would it be parabolic or linear? Would I go the same amount every second?
Linear.
So we turn into a linear increase. Right? My velocity, if it's going the same amount of distance every second, my velocity would become positive or constant. I mean. And if it's constant velocity, what's the slope of this portion? So my acceleration would drop to 0. Fortunately for y'all, I don't have that set up, so you just have to take my word for it. Any questions there? All right, so then the rest of today we're going to look at talking about and look at some other information we can take from graphs. Of course, I don't have the one I'm looking for, so go right here. Now, I have a copy of this actually that I will give to you. Maybe. All right, so I have then a graph, right, that's the same as the one on the overhead. And we're going to look at, initially, right, how do we move from one graph to another? Right, use some stuff we've talked about over the last couple of days. And then some other information. The position time graph, right, we can be used to make a velocity time graph, but then there's some additional information we can get from a velocity time graph other than acceleration that will be beneficial to us graphically. And then we'll talk about how can we do that stuff or use it. Right? And is there a way to deal with the motion of an object other than off a graph? Okay? So initially we'll look at, you have that piece of paper below is a position time graph for a hamster that moves within a long tube in one dimension. And it says, answer the following question regarding this graph. On the graph below, graph the velocity of the hamster as a function of time. Right? So during the first during the first 2 seconds of the motion, what happens to where does the hamster move? It goes from 0 to where? Negative 1.6, right?
Mm-hmm.
So the velocity, right, would be change in position, which is negative 1.6 minus 0 over the time of 2, or negative 0.8 meters per second. Is everybody good there? So on my velocity graph between 0 and 2, I'll go make a line at negative 0.2 meters per second. Or negative 0.8 meters per second. Sorry. Then what happens between 2 and 4 in terms of position?
Doesn't move.
Doesn't move, stays in the same spot. So what's my velocity if I'm not moving? So during that 2 second interval, my velocity is 0. And then from time 4 to 7, what's my change in position? My change in position is final 0 minus negative 1.6, right? Where I started, over 3, or negative or positive 1.6 over 3, which should be positive 0.53. Everybody good there? Then from 7 to 10, my velocity is 0. Right, from 10 to 12, my position goes from 1.2 minus 0 over 2, or 0.6 meters per second. Is that right? From 12 to 16, I'm at rest. And then from 16 to 17, the change in position is 0 minus 1.2 over 1, or negative 1.2 meters per second. Right, slope of this line. So from 16 to 17, negative 1.2. And then till 20, I'm at rest. Everybody good there? So that would be a velocity time graph. You might connect all those little areas. Either way, I think you'd be okay. So that would be the velocity time graph, and that's all you're really asked to do there. So taking that position time graph, using the slope of those different segments, produce a velocity time graph. Could I make an acceleration time graph here? Mm-hmm. How would I go about trying to do that? How are velocity time graphs and acceleration time graphs related to each other?
Acceleration graphs the
Slope of the velocity graph, right, should equal acceleration, correct? So if I looked at all these points, what are my slopes there?
0.
So my acceleration graph, the hamster moves the same speed all the time, right, in this case. Not like getting faster or slower. Everybody good there? And that's pretty straightforward. Now, some other information that we can find or deal with in terms of velocity time graph. And looking more at the velocity time graphs are usually a little bit more useful because we can get more information from a velocity time graph than we can from just position time. So you have this same graph in front of you, kinematics graph. Right? It says basically figure below is a velocity time graph for a test car on a straight track. Initially move backwards in the negative x direction at 20 meters per second, slows, comes to a stop, and then moves in the positive x direction at t equal 2 seconds. What's the average acceleration during each of those time intervals below? So from 0 to 0.5. Right? 0 to 0.5, which would be between this particular, on this portion of the graph. What's the acceleration?
0.
0, right? Change in velocity is 0. So the acceleration equals 0. What about from 0.5 to 1.5, or during this segment of travel?
20.
My velocity goes from final velocity 0 minus negative 20 over the time of 1 second, or plus 20 meters per second per second. Is everybody good there? Then from 1.5 to 2, it's not moving. What about from 2 to 2.5? How do I go about finding it?
It's 40.
Slope of the graph. So it starts at 0, so it ends at 40 meters per second minus 0 over the time, which is 0.5 seconds, or A equals 80 meters per second per second. From 2.5 to 3.5, here, acceleration is equal to, well, the velocity stays the same. And then in the last part, from 3.5 to 4, my final velocity is 0 minus 40 over 0.5 gives me negative 80 meters per second per second. Is everybody good there? Yeah.
What's the saying in the denominator of that?
Here?
Here,
0.5, that's the answer, 80 meters per second per second. 80 meters per second per second. The time here is 0.5. Now, another interesting thing that velocity time graphs will allow us to figure out is how far the object has been displaced during that motion. Okay? If I looked at that square and I wanted to know the area of it, how would I find it?
Length times width.
Length times width, right? Well, in this case, my length is time, and my height or width is in meters per second, correct? So if I multiply seconds times meters per second, what kind of unit do I end up with? Meters. And that will give me displacement on that particular object based on its graph. So if I looked at, I'll start over here between 2 and 4. Okay? For us, I can break that into 3 areas that should be relatively easy to determine the area of. A triangle, a rectangle, and a triangle. Pretty straightforward, right? Now, if I had a velocity that was changing in a non-constant fashion, right? Like when the acceleration wasn't constant, right? How would I go about finding the area under that curve? Could I do it as simply as this?
No.
I could get a pretty good estimate, but to do that really involves what we call integration, right? Which is kind of the opposite of taking that derivative that I mentioned yesterday. We don't do that here, right? That's something you do Mr. Dan's class, right? Or Physics C, right? Where we look at calculus and those tools that we have in calculus to actually study, right? To find slopes in areas. For us, we're going to end up usually with pretty straightforward objects that are going to allow us to calculate the area in a fashion that's pretty straightforward, using things we're probably familiar with. So I'm going to look at this area first. So I'm going to go from 2 to 2.5. Can I find the area of that triangle? Right, and that should be 1/2 base times height, right? 1/2 of 1/2 times height of 40. Right? So 1/4 of 40 should be 10 meters, correct? Then if I looked at from 2.5 to 3.5, which would give me the area of that rectangle, once again, 1/2 base, which is 1 times height of 40. So 1/2 of 40 is 20 meters. And then over here, from 3.5 to 4, I would get 1/2 of 1/2 times 40, or another 10 meters. So the total displacement during that portion of the graph 40 meters. Does that make sense? Yeah.
Okay, wouldn't the middle rectangle just be 40? So you don't multiply it by a half.
Oh, you don't multiply it by half. That's a nice call. That's a nice call. Length times width. Good call, Alex. So 40, so my total then comes 60, right? 60 meters. Okay. Did I start off traveling there? Where did I start off, though? I started traveling in the negative direction, right? So now I'd have to look at, initially, which direction am I moving? If I start at the origin and I'm going at negative 20 meters per second, I'm going opposite, right? So all this displacement here is actually negative. Okay? It's actually negative. So I'm going backwards for 20 meters per second. Right? Then I slowly slow down until I stop. Then I turn around and then I start going back in the positive direction. So the difference between where I started and where I stopped can be found by looking at the total of all those areas. Where those areas above the x-axis are going to be positive and the area below is going to be negative. Can I find this area? It's half the second times 20.
Negative.
All right, so negative 10 meters here. Then this one is half of a second. And my change in velocity, or my height, is negative 20. Right? So during this whole time, I've gone negative 20 meters. And during this whole time, I've gone plus 60. So where do I end up?
40.
At plus 40 meters on that line, right, in relation to my origin. That velocity time graph is really good for giving us displacement. How far am I from the start to the stop? Right? You can figure out when was it that I crossed the origin again. If I go back 20, I come out 10, and this is 40, right? So like at that time when my total displacement up was 10, was 20, and equals a negative 20, that's when I crossed the origin again. Now all this would be positive area that I've gone back in a positive direction. Does that make sense? So looking at that velocity time graph, now after we handle the graphs, right, and deal with those, then we'll start talking about ways we can describe, discuss, talk about the motion of objects. We don't have to have a graph, right, using those kinematics equations that we maybe looked at a little bit the other day in lab, but really haven't gotten into yet. Yeah?
For the base of the rectangle, shouldn't it be 2?
Well, it's 2.5 to 3.5.
Oh.
Right, total time. Right. Does that make sense?
Mm-hmm.
Right, any questions there? Right, so then I have some more problems for us to look at on our own between now, and I think I've got a couple posted up. And that should do it then pretty much for today, other than some problems. Anybody have any questions? Right, so we want to make sure today that we look at how do we make velocity time graphs from position time graphs, how do we find the acceleration from VT graph, as well as displacement.